Okay, welcome back. This is the second lesson on drawing Lewis diagrams or Lewis structures. I had to change out the periodic table here. I think this actually shows electronegativity a little bit better. So let's go ahead and head down to the next set of molecules that we wanted to draw Lewis diagrams for. Right here we have hydrochloric acid, HCl. So yet again, we already know that H has one valence electron and chlorine has 7. So together this is going to have 8. Now we only have 2 atoms, so we don't really have to draw anything in the center, and most likely this is going to be a linear shape. So I will draw the chlorine and bond it to the hydrogen. That takes us down to 6. Now if you think about it, this hydrogen cannot have any more electrons. So all 6 of these electrons have to go around this chlorine. 1, 2, 3, 4, 5, 6. And we are done. It's very easy. Now I want to point something out. This is, I know we're not on geometry yet, but this is linear, which means it's a straight molecule, as you can see. But this is also going to be polar. This side of this molecule has more electrons, so it's going to be a little bit more negative on this side, and this side will be a little bit more positive. Just keep that in mind as we go along here. Okay, carbon dioxide. Well, carbon has 4. The good thing about drawing these is that you really start to know the periodic table very well. Oxygen has 6. Valence times 2. So we have 12 plus 4, 16. Okay. So we'll go ahead and draw the carbon in the middle because that's the least electronegative. If we go back and look at carbon, it's 2.5. Oxygen is 3.5. I always go to the wrong page. Alright, carbon. And then we will bond it out to the oxygen. So that's 1, 2, 3, 4. We have 12 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. The problem with this is that carbon only has 1, 2, 3, 4 valence electrons right now. So remember, we don't have any electrons left to distribute. We're going to have to start drawing double or triple bonds. So on this one, I'll just delete that. Draw a double bond. And over here, I will delete these and draw another double bond. So now this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. Both the oxygens are good, and this carbon is also good. Now let me point this out again. This is actually also linear. See how this is a straight shape? Basically, these electrons want to be as far away from each other as possible. It's all about charges. They're negative, so they're trying to be away from each other. There's no lone pairs in here, so this will be a linear shape. All right, good old water. We've talked about water before. So we have hydrogen, and there's 2 of them. It's 1, but what's 1 times 2? So it'll be 2, plus the 6 from that one oxygen, so we're going to have 8 valence electrons. Yet again, hydrogen can never be in the middle, so it's going to have to be oxygen. Alright, now bond it out to the hydrogen. It's 1, 2, 3, 4, so we got 4 left. And these hydrogens cannot have any more electrons. We're going to have to put these 4 on this water. Okay. Here's the thing. This is actually not linear. I know this CO2 was linear and it had 3 atoms. This has 3 atoms. You're probably thinking, why is this not straight? Well, it's because of these. These are called lone pairs. That's one lone pair of electrons. This is another. A lone pair of electrons is just a pair of electrons that's here but not bonded to another atom. And these actually have a little sort of like cloud of negativity that's right here. See how unhappy that is? And these push these down away because there's only one electron here. So this is not linear. It's called bent. We're going to go over all this more, but this is just a good introduction. Okay, so that was water. Let's move on down. All right. Boron. Boron's a little strange. Let's go look up boron. You know, it's in that group 3. Electronegativity is 2.0, so it has 3 valence. And these chlorines have 7 times 3. So it's 21, 22, 23, 24. This is boron trichloride. So we're going to draw the boron in the middle. Remember the electronegativity is 2. Then we'll draw it out to bond it out to the chlorines. Okay. Oops, I had 24. 1, 2, 3, 4, 5, 6. So I have 18 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right. This is actually something called trigonal planar because it's like this little triangle, but it's also flat. It's a flat triangle. Now I added in these polyatomic ions. Remember, these polyatomic ions are from the last unit when we talked about ionic bonding. The thing is, SO4, 2 minus, is still bonded together covalently, but then this will bond with some sort of metal to form an ionic compound. These are definitely a little bit more difficult, so I wanted to get into these a little bit. So first of all, we just do it like normal. Sulfur. And if we look at sulfur, it should have 6. And oxygen. There's 4 of them. So you can get my math on here. 24. So you're like, well, there's 30 electrons. Actually, we got to keep in mind that there's actually 30 electrons plus we have to add these 2 more. If there's a minus charge here, it means there's that many more electrons. So instead of 30, this is going to have 32. Okay? All right. So we're going to draw sulfur in the middle. Then we're going to bond it out to the oxygen. Normally, if you have 4 bonds, it's going to be this sort of square shape like this, where there's 1 on each side. All right. And actually, this is called tetrahedral, but we'll get into that later. That's 32, so we have 1, 2, 3, 4, 5, 6, 7, 8. So we're down to 24 already. Now, let's go ahead and put 1, 2, 3, 4, 5, 6. Then we keep going. And there we go, 6. And actually, that is complete, except for one thing. Whenever you're drawing these ions, you then have to draw a little square around it, like little brackets, and put the charge on it so people know this is a polyatomic ion. So keep that in mind. That's the only difference besides adding these electrons and drawing these brackets. All right, the next one is carbonate. If you remember from the last unit, polyatomic ion, 2 minus charge. So C has 4. Oxygen has 6 times 3. That's 18 plus 4. plus 2 more. So really we have 24 electrons. Okay, this one's a little strange, so we'll draw the carbonate in the middle here. Then we'll draw out our oxygens. Bond it to the oxygens. Oops, I said we had 24. So we're already down 1, 2, 3, 4, 5, 6. We got 18 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then over here, 13, 14, 15, 16, 17, 18. Okay, yet again we have one little problem here. The problem is this carbon has 1, 2, 3, 4, 5, 6 valence electrons. And this carbon actually wants 8. So what we could do is draw a double bond to it from one of these oxygens. Now this is actually a little bit different. And yet again we would draw a little bracket here and we would draw 2 minus. And that's fine. But there's one thing you should understand about this. This is something called a resonance structure. What that means is I can draw this double bond on this oxygen, or I could draw it on this one, or I could draw it on this one. And so normally, sometimes you'll see where there'll be carbonate, but there'll actually be 3 different diagrams to show that there might be 3 different structures. We just don't know where that double bond is. Also, sometimes, I'm just going to get rid of this bracket so it's easier to see. Instead of a straight line, it'll be a dotted line. That dotted line tells us that it could actually be anywhere. It could be right here, here, or here. So, it's called a resonance structure. That's when you can draw different Lewis dot diagrams, and they represent the same molecule. And also, really, we're not going to get into this right now, but there's actually not really a double bond on one of these per se. That electron is sort of delocalized, but we're not going to get into that. It's a little bit more advanced. All of these bonds are actually equal in strength. But anyway, I just wanted to show you resonance. Now this last one here is definitely a little odd. That's why I threw it in. So this is phosphate. We know oxygen is 6. So there's 24 oxygens plus 3 electrons here, plus the phosphorus, which has 5. So that's 32. All right. Now, let's go ahead and draw the phosphate. The phosphorus in the middle. Oops, remember we have 32. I always do that. And let's go ahead and draw the oxygens connecting to it. So 2, 4, 6, 8. 24 left. Now, let's go ahead and put in the electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And that's basically the structure. Of course, I would draw these little brackets, and then I would draw 3 minus. Now, what's slightly odd about this, and I actually looked this up to verify all of this, is apparently there's a double bond between one of these. And yet again, it's sort of a delocalized electron, so not all these bonds are actually about the same strength, but you're probably thinking, why? Why is there this double bond here? And this makes this phosphorus now have 10 valence electrons. And That just makes no sense. Well, I put this in here because I wanted to point out one thing. If we look at phosphorus, see how this is period 3 here? 1, 2, 3. Phosphorus, sulfur, silicon, these elements over here can actually have an expanded octet. They can go up to 10 or 12 sometimes. They can do that because these d orbitals, which are right here, are empty. So think of it as sort of like an empty little pocket that you can put extra electrons in. Now these up here do not have d orbitals. Remember, this is energy level 1 and 2. So there's no d orbitals up here. It's down here that they're empty. So sometimes, yet again, in chemistry there are exceptions. Now you're not going to get that on a test at the high school level, hopefully, at the intro chemistry level. But I definitely wanted to point it out because I would just want you to realize that if you continue on in chemistry, there are exceptions to a lot of these things. Yet again, it's like the Pirates Code, sort of general guidelines. That way, when you get to AP chemistry or more advanced chemistry, you'll start realizing all of these exceptions, and then you're going to get into the reasons why. We're not getting into the reasons why right here because it can get complicated. So, we are now done with drawing Lewis structure diagrams. In the next video, we're going to talk about polarity. After we talk about polarity, we'll talk about the actual shape of molecules, which is VSEPR structures, and then we will be done. All right, I hope that helped you out. Thanks again.